I'm very pleased to welcome Jochen Renz as an invited speaker to KR 2021. Before this talk, I was contacting Jochen and I was asking him whether there was anything particularly interesting about his life and his work that I should be mentioning, but his reply was that he wanted to have as short as possible an introduction. So I keep it as short as possible. I want to introduce Jochen as the invited speaker. Jochen is a professor at ANU in Australia, in Canberra, and he's been working for many years, as I'm assuming most of you know, on spatial reasoning with a particular interest in angry birds and applications in the real world, which is also what he's going to talk about today. So without any further ado, Jochen, the floor is yours.
Thank you very much, Michael, for the short introduction, and thanks for the invitation to talk today. I'm actually very sad that I cannot join the conference at home. I haven't been traveling in 2 years almost. Normally I travel a lot, but the last 2 years I haven't been traveling. But there's one little benefit of doing it from Australia. It's that I always have issues joining these invited talks at 9 o'clock in the morning. And now I can give my talk at 7 in the evening, which is very nice. So I don't have to get up as early as the people anymore. Okay, but let me start. So today I want to talk about my research on spatial and physical reasoning. And particularly about angry birds, how we use it for angry birds, and then basically do a loop from angry birds, how we got to angry birds, and to open world, which is kind of where it gets even more challenging than angry birds is already. So I want to start with a little, oops, hang on. Okay, I want to start with kind of a vision, a challenge we have that we want to solve. We basically want to enable AI to act safely in a physical environment. All right, so the key to a physical environment, by saying acting in a physical environment, the particular actions I mean are physical actions. Right? A physical action is basically an action performs, interacts with the physical world. For example, here I have this glass of water, right? And grabbing this glass of water and putting it to my mouth and drinking it. And you can think about it, when you do these physical actions, the outcome of these depends a lot on the physical properties of these objects and the environments that you interact with. And the problem is that these physical interactions, for example, the mass of this glass or the friction between the glass and my hand, are unknown. Right? I usually don't know this just by looking at things. I don't know their physical properties. Right? And that gives us a problem when we want to evaluate these physical actions and select physical actions, because basically it means that we don't know the outcome of these actions. We cannot simulate the outcome of the actions in advance, and we cannot calculate it, because in order to simulate it, we need all these physical parameters to exactly calculate it and simulate it. Right? And that's a problem. And basically, if I vary my action a slight bit, I mean, I can grab my glass like this or like this or like this. There are like infinitely many ways of doing these interactions, and each of these different physical actions might lead to a different outcome, which is kind of unknown in advance. And also we know that the world and the world we live in is usually continuous. And most of these methods that we're using in KR are not continuous, right? So continuous means there might be infinitely many variations of the actions, infinitely many possible actions. And so what we're trying to solve is we try to solve this problem, right? Doing physical actions, interacting with the physical world, and doing it in a safe way. And safe means we know that the actions we do, they have no weird side effects. So don't, for example, I'm not actually accidentally spilling my water over my laptop and cannot keep the talk anymore, right? Or something like this. So I need to know this. So an AI that interacts with the world cannot just do any actions. It needs to be safe in doing the interaction that no harm happens. And what we're doing here is we want to do physical reasoning, right? In KR, we're doing reasoning. Specifically, I have a spatial reasoning background and did a lot of reasoning. So we think that reasoning, physical reasoning, can be used to do all kinds of these interactions in the physical world, and to determine good actions. For example, it could be used to infer the outcome of a physical interaction, It could be used to select a particular physical action that receives a desired outcome, or to infer, for example, what action caused a given outcome. So I'm going to show you a few examples to make it clear what I mean. And I guess you know all these things. So I guess the simplest example is this mousetrap game here on the bottom left, which is quite a very old and popular kids game. It works like this. You basically have like a little boot here, and you pull this sign, and then the boot kicks this bucket, and then the bucket has a little ball, and the ball rolls down the stairs, and then it goes into this pipe, and so on. And somehow it triggers this ball up here to fall into the bathtub, and then down onto this what's this called? This wedge or whatever you call it, and then this jumper jumps into this bucket, and by jumping in this bucket, this thing shakes, and this trap comes down and traps the mouse that is sitting. All right, so this is kind of like a sequence of physical actions, and so we need, if we predict actions, for example, we need to predict by looking at this game, what happens if I kick this boot to the bucket, what happens then, right? And I think everyone, just by looking at this, is able to roughly determine what the outcome of your physical action is. It gets a bit more complicated when you look at this game here. The game is called, I think it's called Villa Paletti. You have like these stacks of, you have these little sticks, and you need to place these sticks, and then later you need to remove these sticks. One by one, you need to remove them. And so the question is, for example, if I remove this yellow stick here, I don't see my mouse at the moment, here it is. This yellow stick here, what happens? Can I remove this? Does this whole tower fall down or not? Or what happens if I remove this red stick here? Does my tower fall down or not? So basically, what is the outcome of this physical action? And this is something you can estimate, because we all have a very good idea how the stability works, center of mass, and we can estimate, this tower is like that heavy, and it's slightly towards the back, and if I lift this red stick, then maybe it falls over. So we can guess that. Right, here in the Angry Birds example, I assume that most of you know how Angry Birds works. It's basically you have these green pigs, and the task is to kill these pigs, and you have to kill them by shooting these birds from the slingshot here. And so now this is the action you have, right? You shoot this bird from the slingshot. What's the outcome of this action? Can anyone guess what the outcome of this action is? I know it's not a two-way thing, and you probably cannot say. But when you just look at it, you can guess like, it goes maybe like this, and then you actually don't know. You don't know how heavy it is. You don't know what the trajectory is, right? Maybe it goes like this. Maybe it goes like this. You don't really know what it does, right? With a bit of experience, you can maybe say, maybe it goes like this. I don't know, But we basically don't know. It's hard to tell. So if I really execute it, we can see that it hits this TNT, and then this ball jumps over, and this ball goes down and hits this TNT, and then it continues, and this boulder here rolls down and then kills the big one, and even the next one, and so all the pigs are dead, right? And so the game is basically solved with one shot. But who would be able to predict this, right? By looking at this particular action, are you able to predict the outcome of this action? I wouldn't be, at least in a complicated situation like this. Maybe you are, if you're very experienced. Good for you, but I think usually it's very hard to predict these outcomes of these physical actions. The second example I wanted to show is selecting a physical action, right? So previously we looked at one action, but as I mentioned before, there are like infinitely many actions that you need to look at, right? So how do you select the right action? And in a simple case, it's, for example, this Jenga game here, which is not too hard. There are not that many actions you can do, but it's still quite difficult. Here's a mini golf example. You need to somehow hit the ball so that it goes into the hole. And there's also like a lot of different actions, particularly if the ball needs to bounce, and then like this obstacle course or so. Or here, like an everyday example, this fridge. Let's say you want to get this full cream milk in the back with a red lid. What would be the action to get that out? And now imagine you have this robot, this household robot that has to do that. What would the household robot do? Right? How would it get this red milk in the back of the fridge without causing like a major disaster and everything landing on the floor and spilling out and all that? Right? Another example is this stacked this palette with these boxes, which are not very nicely stacked. And the task could be, for example, remove this one or put another box on top or something like this. What actions do you do? All right, and here in Angry Birds, we have an example where we have like, I think it's like 1, 2, 3, 4, 5, 6, 7, 8 birds. And you basically have these 3 pigs that you need to kill. What action do you select with the first one? What can you already predetermine in advance what action you do with the second one and the third one? And then make a plan how to solve this with the least number of birds possible. Right? So that's the action selection, and this is also very hard. The next example I want to give is identifying what physical action costs a possible outcome. Right? And this is another problem where we think we can use spatial and physical reasoning for it. So here, in this example, for example, this bridge, this bridge came down. What could have possibly happened? What action could have possibly happened that brought this bridge down? And if I remember correctly, I think like a truck was driving into one of the pillars or something like this. In this Angry Birds case here, we have like a before and after situation. So what action, I put this cloud here so you cannot see which action it was. So what action caused this tower to collapse in that way? So what was the action? Well, here I have this setting here. This is the before state, this is the after state. Which action caused this after state? It's very difficult, right? Even for us humans, it's very difficult to do. And this is kind of the things we want to use physical reasoning for. We want to be able to solve. Right. And as you might have seen from this example, physical reasoning is quite hard. It's quite hard for humans. It's even harder for AI. And there are many different reasons. Like, for example, one is that the world is very complex. It has like basically almost like infinite granularity and precision. AI, just like us, we can only deal with the information that's available. And for AI or robots, it's typically perception through computer vision, radar, infrared, laser scans, and so on. And this is usually noisy, and it doesn't give us all the physical parameters that we would like to have. We could also use some background knowledge. For example, we know that water is that heavy, and this glass is approximately that big, so it might be like this heavy also. Right? So you can estimate using background knowledge. But basically, you don't have enough information to simulate these actions, and all consequences must be inferred using other methods. Right? And as I mentioned in this example where you have like these multiple action sets or almost infinite actions, so even if everything is known, you would have to simulate a lot of actions to find a good one. Right? So the action space is very large, typically continuous, and that makes it very hard. And as I was showing in this Angry Birds example, you typically have like a sequence of actions that you need to do your task. And basically for every action, you don't know the outcome of it. So how can you plan ahead and think what is my action sequence going to be? Right? So it's a very hard problem, but it's a very, very important problem. And I'm going to show you some examples why to make it clear why it is such an important problem. So our goal, as I mentioned in the beginning, is basically we want to develop AI that can successfully and safely interact with the physical world. And that does that purely based on the perception. The AI needs to be aware of the consequences of the physical actions. And I mentioned before, it's very hard to predict the outcome of the physical actions, right? And it needs to select its actions in a way that there are no unintended side effects. Right? I don't want the agent to get this milk out of the fridge and all the apples and the apple juice or whatever is in front of it falls down. Right? So basically, there shouldn't be any unintended side effects. The AI should be able to predict what's going to happen and pick actions accordingly. Basically, we want robust AI, and that is essential if we want to safely live and work together with the AI. Right? So basically, if the human is in the loop, if it's not just the AI somewhere on its own, but if humans are involved, right? And as humans, we're very good at this. We have a lot of experience and intuition. We basically learn it from the start, like infants, they learn this physical reasoning capability from very, very young age and build it up. And we talk about this a bit later as well. And but AI is not very good at doing that still, and this has some consequences. So I give you some examples. Here, for example, some of the robots that many of us have in our homes are these vacuum cleaning robots. And like these robots, just like self-driving cars, what they try to do, they are in the physical world, but what they try to do, they try to stay away from everything, right? They try to keep a distance, because if they keep a distance, it's kind of usually safe. Not much can happen as long as they stay away, right? But in this case, like this poor woman was lying on the floor and she has long hair, and the robot, of course, sees the head and stays away from the head, but the hair is so long that it's longer than the safety distance, right? And the hair was sucked into the robot. It's like, of course, a terrible situation, right? You don't want a situation like this to happen. You want the robot to do physical reasoning and to avoid a situation like this. Another example, sorry that I show all these traumatic examples, but what I want to kind of show is that this research can save lives, which is, it sounds important, right? And it is important, I think. So there's this robot that crushed this poor worker at this Volkswagen plant, right? And when you think about it, look at here, the robot is usually kept in a cage. You see that? The robot is usually kept in a cage. So these robots are so dangerous, they need to be kept in a cage, right? Because we cannot trust them. They can't do physical reasoning. If this robot could do physical reasoning, maybe we don't have to keep it in a cage, right? Then we can have it in our household. But you don't want to have a robot in your household and you have to keep it in a cage. That's so dangerous, right? We need to do something about it. Here's an example where it's clear the physical reasoning went wrong. There was an accident, and probably it was like worldwide in the news. This Uber car was basically didn't see this woman on the bicycle, like walking across the road, and here you can see basically the physical reasoning went wrong right here, because the car couldn't recognize as a pedestrian or person, instead alternating between classification of vehicle, bicycle, and other. I'm not sure what difference it makes. If it's a bicycle, it will also crash into it, right? But anyway, it couldn't correctly predict her path and concluded that it needed to brake just 1.3 seconds before it struck her. Right, so basically, this is physical reasoning gone wrong, and this is what we're trying to avoid. Right, so basically, doing this physical reasoning, we can save lives and have contribute to having safe robots in our life and safe AI. So what are we doing about that, right? What can we do about it other than lifting this glass? So the problem is that every physical situation is different, right? So it's very hard to generalize. So I've shown quite a few examples, and each of these examples is different. And something that works in one example does not necessarily work in the other example. Or for example, Angry Birds. You have these different game levels, and every game level is different, even though it's all an Angry Birds game, right? Every game level is different. You can train on one and can master it, but that doesn't mean that you're good at the next one. Right? So every situation is very hard. It's very hard to generalize, and that's the main reason why deep learning, for example, which is currently extremely successful, and it's kind of all these problems that we have been looking at is now deep learning is kind of solving, and but this problem cannot be solved by deep learning at the moment. And I think that this is an opportunity for KR, right? This is something that we can contribute to. This kind of falls in our expertise to work on these problems. And KR has been working on this for a very long time. For example, qualitative physics has been very, very popular in the 70s, 80s, and 90s, the last centuries, and many famous KR researchers worked on it. Right? And it kind of was trying to do what I was describing before. And out of these examples that I gave before, I think the mousetrap example could be perfectly modeled by these traditional qualitative physics models, and it could be solved by this. About these other examples, I don't think it would work, these traditional qualitative physics approaches, but it was a very popular area. And what happens very often, the area is kind of had like different components, different problems that needed to be solved, and each of these problems kind of evolved in its own area, more or less, right? And so now there are all these different areas that kind of result from qualitative physics, and qualitative physics is kind of not there actively anymore. Right? There are very few people are working on that still, but it's not kind of mainstream KR anymore as it was like in the 70s and 80s. And one of these areas that came out of qualitative physics is qualitative reasoning, and specifically qualitative spatial reasoning, which is the area I have been working on for a long time. And this area is very, very important for physical reasoning. Because when you think about it, let's say you're trying to describe the physical world, right? And you think about what these actions do in the world, right? So it's basically like this. You describe the world, you describe kind of the state of a world, and you can describe it in terms of the physical properties of the world, also like spatial properties of the world, also some physical properties, but the spatial properties, like what is the location of this class, what is the size of it, how full is it, and all these things you can describe. And then you apply a spatial physical action to it, and then something changes. And what changes is typically like the spatial properties of your scenario that change, right? So you can basically describe how was the world, the spatial properties of the world before the action, and the spatial property of the world after the action, right? And then basically by describing these changes of your world using these spatial properties, you can express the change, the effects of the actions, and what the actions do, right? So basically these physical actions are kind of strongly connected to the spatial properties and spatial representation, spatial description of the world, right? And what we're hoping is that by using spatial reasoning and by basically reasoning about these spatial representation, about these spatial properties, that we hope to be able to do physical reasoning, right? And because of that, I want to very quickly give a little introduction about qualitative spatial reasoning, qualitative spatial relations. But this is just like a 2 or 3 minute intro. Most of you probably know it. If you don't know it, you won't learn it in this talk. But so this is just a quick overview. So basically, what we're doing, and this is why this qualitative spatial reasoning is ideal, because I mentioned that we have this continuous infinite world with all these many actions, right? And it's very hard to look at all these interactions. So in qualitative reasoning, what we're trying to do, we're trying to basically create equivalence classes of things that we consider to be the same. We don't bother distinguishing them. We say, oh, they are the same, right? And that's why this is so useful, because this continuity, we can basically break it down into the pieces that we think, the distinctions that we think are important, right? And we do that by first defining a domain. What is the space we want to deal with? So it could be, for example, a line or a plane or 3D space, which is of course resembling the physical world. Then we have the entities that we want to look at. These are typically points or maybe line segments or n-dimensional regions or maybe lower dimensional regions. And then we can define relations, and the relations are basically k-array relations between this on this domain, right? But mostly we use binary relations. I mean, you all know spatial relations. Something's to the left of something, or to the right, or on top, or it's far away from something, or it's heavier than something. Is that a spatial? Probably not. But all these different relations, it's larger than something. So what we do is basically we distinguish what we call the basic or atomic relations, so that we don't have like any arbitrary number of relations, but we basically focus on these basic relations, and they have this property that they are jointly exhaustive and pairwise disjoint, which means that the union of the basic relations covers all possible tuples, like all possible relations, and they're pairwise disjoint. That means two base relations don't have any common tuples, right? So they're basically disjoint. So now, when you have binary relations, you take two entities, whatever, my phone and this class, they can only have one of these. They can only be one of these spatial relations, but not in multiple of these basic relations, right? And what we do, we typically select meaningful relations. As I was mentioning before, we have these equivalence classes. So relations that are meaningful and useful for describing properties of the world. Like typically we like topological relations, direction relations, distance, size, occlusion relations, movement relations, shape relations, and so on. Like all kinds of things that the person who introduced them basically thinks are meaningful. And I have here a few examples of them. Like here are on top these circles, these are the RCC relations, region connection calculus. These are topological relations. Then these are the interval relations, interval algebra, where we have like two intervals on the directed line, and it can be before, it can meet, or it can overlap, and so on. And here is like the interval algebra in 2D. Basically, it's called the rectangle algebra. We have like rectangles on a plane, and we take the projections of them on the line, and then we get these intervals. The projection basically reaches the intervals, and then we look at the intervals on the x and y axis between those. Over there on the right is the star calculus, where we basically have we split the plane using different lines, and these lines create like these sectors, and these sectors correspond to the relations we use. And depending on the application, we pick lines in a different way. Right? So, and these relations and their properties, that they're often defined using theorems and axioms and first order logic, which obviously allows us to do some reasoning about them. Right? And so the reasoning basically works like that. We take these spatial relations between entities, and then there are different reasoning tasks. We can basically try to infer yet unknown relations, like have the relation between A and B and between B and C, but not between A and C. And I try to infer this relation, or I try to identify inconsistencies, try to eliminate impossible relations, and so on. So we have these operators that we define on these relations, and applying these operators allows us to do reasoning. And in the past, I've done a lot of this kind of reasoning. For example, I looked at theoretical properties of reasoning, spatial reasoning. I developed efficient reasoning algorithms. Or I was also proposing some new calculi, for example, star calculus I proposed. And one thing that's very interesting is like trying to combine different calculi, basically looking at, for example, topology and distance or direction at the same time. Right? And so I've done lots of interesting stuff there, and it's worth reading some of my old papers if you're interested. And I'm of course still working on these things. But what happened in 2011, ICHCA 2011, maybe some of you were there, there was the workshop on benchmarking applications of spatial reasoning, and that changed a lot of things. And this was one of the most memorable workshops I've ever attended. It was quite special because we had so heated discussions. We were yelling at each other, and if I remember correctly, we were even calling each other names. Right? I've never had this in any workshop, so it was a lot of fun, and it was very controversial. And so basically, we decided about what can we apply spatial reasoning, what can we do about it to make it more useful. Lots of communities having these kind of discussions, right? And what I took out of this workshop was that I started to use AIBIRDS for spatial reasoning. Right? So that basically, I thought AIBIRDS is a very interesting application example where we can demonstrate that spatial reasoning is useful. And when you look at this level here, for example, it's clear that you have to do reasoning. For example, you can, where's my mouse? Here. For example, if you, how do you solve this? Right? You have this tunnel where something happens here. Basically, if this ball rolls down, it explodes this TNT, and then these balls go up and explodes this TNT. And basically, by activating this ball, you kind of destruct this half of this, what's called a castle. And then by shooting over there and having these boulders roll down, you can activate this. So basically, by destroying this part of the castle, you can indirectly also destroy this part of the castle. Right? So this involves like some spatial reasoning, and so these samples, they led me to believe that AIBIRDS is actually a very interesting application of spatial reasoning, and that's kind of how it all started with AIBIRDS. And the first thing that I realized is that it has some implications for spatial reasoning research. So there are a few things that we haven't been doing before that are kind of very important if you apply it to a domain like this. So first of all, in AIBIRDS, we look at the screenshots, right? It's like a video that we get. And when we have a video and we need to extract these spatial relations in real time, then it might not be so easy to use all these different spatial relations that we developed, right? So for example, we have to use computer vision, and computer vision can give us these minimum bounding boxes of objects very fast, right? So the consequence of this was basically we developed like a spatial calculus for dealing with bounding boxes. This is together with Tony Cohn. It's called the comprehensive relation calculus or something like this. Basically, we looked at all the possible relations we can extract by just looking at these bounding boxes, and then we came up with distance, direction, topological, all kinds of relations that we can extract very fast. And in addition, we developed how we can use these bounding boxes and extract the real shapes of the objects. So we developed an algorithm that allows us to extract the real shape of objects from these bounding boxes. So basically we can, by using very fast computer vision, we can get the real shape of objects, right, and do some reasoning. The other interesting observation was that most of these spatial calculi that we looked at in the past, they actually assume like some kind of bird's eye view of the world, right? You have the plane and you look at the plane from the top. But when using Angry Birds, we realized that we actually need a human eye view of the world, right? But that means we need to look at the world from the side and not from the top, if we use it like in these human applications. And the one difference of the human eye view instead of the bird's eye view is that you always have gravity, right? Gravity is always there, and you need to deal with it. So what we did is we developed a new spatial calculus that can deal with gravity, which is an extension of this rectangle algebra. Like, and when you look at the bottom right here, these are two situations that in the rectangle algebra are exactly the same. But this one, for example, is not stable. It falls down here, while this one is stable. So we want to be able to have a distinction between these two situations. So what we came up with a new calculus that basically similar to the interval and the rectangle algebra. Instead of using just the two endpoints of the interval, we add a third point, which is the center of mass. And then we can say basically, oh, this rectangle does not overlap the center of mass, but it's only on one side, and that's why it's not stable, it falls down. Right? So what this allowed us to do, it allowed us to do a qualitative stability analysis of a structure. So we just need a support graph and then have these rules like these typical reasoning rules. Whatever, if the support is only on one side of the mass center, then the structure is unstable and will fall to the other side. Right? So we can do this qualitative stability analysis. And so we did quite a bit with this qualitative stability. And in the beginning, our algorithms were quite simple, but in the end, they were quite advanced. But obviously, using just qualitative reasoning, you cannot determine stability because it depends on the internal mass distribution of a solid object or things like this, which you cannot do using qualitative reasoning. But basically, we did it as much as we could by combining support and things that are on top and computing the center and estimating the center of mass of multiple objects and so on. And so basically, it got more and more sophisticated. But what we did with this was basically we were able to predict consequences of physical actions in Angry Birds, for example. We say like, okay, here, let's say we shoot at this block here, and this block is hit and it's gone. What happens then? It means like this block is unstable and will fall down, and then this block might be unstable and fall down, but our calculation shows that it's not because the center of mass of it is supported here. Right? And so we predict that basically only these two blocks will be affected, and when you do the shot, this is actually what comes out. Right? So you can basically use the stability analysis to get the mass. And another interesting thing was when you have computer vision, and normally it's easy to detect known objects, but if you have unknown objects, how do you detect them? You have these edge detectors, you have all these edges all over the place, but which edges are an object? And what we can do is when we have these two objects here on the right, and we see, oh, this is unstable, but it cannot be unstable. That means there must be another object here. So we say, oh, all these edges that we see here, there must be an object. Right? So basically using this method, we were able to detect all objects in Angry Birds by just hard coding the piece. Then we also have, for example, we use the stability method to create stable structures from sketches and so on. But what we realized is that basically this Angry Birds is not just good for spatial reasoning, but it's very good for physical reasoning. And it meets all these. It has the same difficulties that I mentioned before that physical reasoning has, right? You only have visual perception, you have this huge action space, you have no forward model, which means your outcome of action is unknown, and you have a sequence of actions to complete, right? So we were basically saying, oh, this is like basically a very nice, simplified and controlled environment that can be used for physical reasoning research, right? And the nice thing is that we don't have to worry about computer vision, because computer vision is kind of simple, and we also don't have to worry about occlusion and these things. So we can basically focus on the physical reasoning bit, right? And the hope is that basically using this kind of research, we can go from these clumsy robots that we have then to like some robots that can kind of safely interact in the physical world, right? In the hopefully not too distant future. So what we did is we came up with this Angry Birds AI competition, where the goal was to build an AI agent that can play new Angry Birds levels as good as the best human players, right? And the important is that we have new Angry Birds levels, because if you use existing one, you kind of hard code a solution or cheat. And so we set up this competition. We built some sample agents, we add the computer vision and all that, and we offer this competition. And the competition is now held annually. The next one will be at ICHCA 2020 in Vienna. And so far we had over 60 teams that participated, and many different approaches, which is very interesting. And what's also nice is that the source code is most of these participants, or most of the good participants, is available. Particularly all the past winners and good agents all available, so you can build on that. And we also test if we can already do physical reasoning or solving Angry Birds as good as human players. And we have this after every competition, we have this human versus machine challenge where we compare with human players, which are basically just ICHCA participants. Right? So it's actually not the human, it's ICHCA participant versus machine challenge. So how good are these AI agents already? This one we've seen already. This is actually a real example from the competition, but this agent is actually not so good to calculate this. If you look at this, what the agent did, it was actually just trying to shoot this at this peak, and then just all happened. Right? It was just a coincidence. But this one is a nice example of physical reasoning. When you look at this, how do you solve that? You cannot reach this peak down there. You have to somehow reach it indirectly, and it's very nicely how it's done. So basically, the agent directly shoots at this block here, at the wood block, and as you can see in the next shot, and brings the it takes a bit long. You can see that I talk about this. This is also a nice level. Here, the agent is clearing the path to kill this pig down there. And so it first removes this glass, which the block up there cannot go through, and then it hits the block. So there's some nice physical reasoning that these agents can already do, right? It's actually quite impressive. Some of these shots are quite impressive, what they can do. Okay, here is the list of winners. And when you look at this list of winners, you will see that most of these, the best performing agents that use kind of similar methods. They use like different strategies, different heuristics, and they have a way of selecting which strategy to pick in a given situation, right? And very often the winners, they took the previous agent and improved some things. For example, here this Eagle Wings agent, they improved the heuristics of the data lab and fine-tuned them using learning approaches. A significant improvement was Bamberg's agent from Bamberg University, where they're really able to plan ahead. They have like rule-based reasoning using qualitative relations, and they can actually plan ahead. And the shot on the right that you saw, where the agent first removed this class so they can kill the pigs, that's from kind of this agent. And some other notable mentions are here, also some KR agents, which uses logic programming, based reasoning, answer-set programming, or this one from TU Dresden uses simulation and reasoning combination of it. So what we saw is that many different approaches have been tried, and I encourage you all to try your approaches to solve this problem. But so far, qualitative reasoning, heuristic simulation, and combination of these work best. Machine learning didn't work well so far, but machine learning was used to optimize the parameters, optimize these heuristics and selection. Right? And what's also interesting is agents improve every year, and it's even possible. It's like some of their code, like for example, the Bamberg team, they have like 20 students involved, and they have this massive code, but they have the code open source, right? So they can just download the code and focus on one of the things and improve one of the things. And the winner from this year, for example, just took the Bamberg code from last competition and improved the shot selection, like which shot is next, right? The order of the shots and stuff like this. So you can basically have one person team and be very good. But of course, that probably doesn't solve the big challenges that are still there. So how does AI compare with human players? So in 2016, there was this paper where they asked AI experts what they think, which problem will be solved and where AI will overtake humans. So in that survey, the easiest problem was Angry Birds down here, and they estimated that like in 3 or 4 years or so, it will probably be solved. That was in 2016, right? So what's the reality? So basically, this human versus machine challenge, we have like 4 Angry Birds game with 10 teams, 10 minutes to solve, and around 10% of humans, they can solve all 4 levels, and the best AI agent, they only solve 2 of them. Of the games, right, which basically every human achieves more or less. So it's a very long way to go for AI. So the question is, what can we as the organizer of this competition do to bring the AI closer to this to human level performance? So one thing, we want to discourage the greedy shooting, which most agents are doing. So we develop these deceptive game levels where greedy shooting doesn't lead to a solution. So for example, here, if you shoot with this bird here, then all this falls down and blocks the access to the bird. So basically what you have to do, you have to waste this bird and then shoot with a yellow bird that goes to both of these and hit it, right? Or similar here. And we did this in 2018, and it has an immediate consequence, immediate impact. In 2019, we had 2 agents, AIBIRDS and SimbaDD from Dresden, that were able to think ahead and solve some of the deceptive levels. Right? Another thing, I mentioned that deep learning agents are not so good. So what we do is we provide now unlimited and diverse training data. We have this competition where we encourage people to procedural content generation and to generate these Angry Birds levels. So using these, we basically now have like unlimited number of Angry Birds game levels that we can use. And we have built this integrated framework where we can add all these game levels as they're basically generated, and we solve them. And this is all freely configurable. We speed it up by 50 times. And we also have alternative representation. So you don't need to use computer vision anymore. We have kind of some symbolic representation of the objects. And so now this can be used, and this is very, very simple to train or test your agents, right? But the problem is that this is all based on science birds, and which is a clone of Angry Birds that allows us to do all these things, which in the competition we use the original Angry Birds game, which doesn't allow us to do. So we might change our competition over to this. The third thing that I think is very interesting, when you think about it, these physical reasoning capabilities that you need to solve these Angry Birds levels, there are a lot of different capabilities that you need, right? And they're all somehow mixed up. Somehow you need this or this or this, or maybe multiple at the same time, and that might lead to the problem being so difficult and so hard to solve. When you think about, I mentioned it before, like infants, they learn these individual capabilities one by one from the very early stage, and then they have lots of experience interacting with the world and improving these, right? And the idea is, what if we could do the same thing for AI agents too, right? We might achieve the human level physical reasoning performance. So what we did, we identified these physical reasoning capabilities, these individual capabilities that we think are important for playing Angry Birds. And you can find this by searching Phy-Q on archive and GitHub, and you can use it. So we identified these 15 capabilities. For example, rolling, falling, bouncing. You have to be able to deal with relative weight, relative height, or shape difference. You have to be able to do non-greedy actions, or do a structural analysis, or clearing paths, which is kind of thinking ahead, and all these things. So for all these capabilities, 15 capabilities, we created altogether 75 templates. I have like one template to here. And for each template, we can automatically create an arbitrary kind of number of different games that more or less follow this template structure, right? With slightly varied setup and location. And what we did is we compared the performance of human players and several learning agents and past competition winners, which are mostly heuristic agents, and also random agent on this. And we tested 2 things. We tested local generalization. So basically, if you use the same template, right, you basically learn on some instances that are generated by this template and are tested on instances that are by the same template, or broad generalization, where we say you test some of the templates for the same capability and are tested on other templates of the same capability. Basically, are you able to learn these capabilities and generalize the capabilities, right? And here, this is very interesting. And I think this offers a nice explanation what we see in Angry Birds at the moment. So in local generalization, so of course, the heuristic agent, they cannot learn, but we just use their performance, like the average pass rate. But these were the two best deep learning agents we use, reinforcement learning agents. This is DQNH, the variants of DQN agents that work best. And they are actually very, very good at local generalization, right? But they're very bad at broad generalization. So at broad generalization, they are quite bad. They are about as good as this is the naive agent that just randomly shoots at peaks. And but some of these agents, they're much better than these, right? They can do quite well. But when you compare humans, they have like 82% pass rate. And what's really interesting when you look at these 15 different capabilities here, you can see that these simple capabilities, like most of these heuristic agents they can do. But some capabilities, for example, number 4 and number 13, is only AIBIRDS is good. And this is the clearing path, and this is the rolling. And these are some kind of like key capabilities in Angry Birds. And we believe that because they can do these things, they are actually able to be so much better than in Angry Birds, right? So that's why we think that they are superior than other agents. But what we see is that all agents are much worse than the humans, except for the most basic capabilities. So basically, in order to achieve human level performance, we need to inform the performance in each of these different capabilities. And then we need a way of combining these capabilities to be able to then deal with the whole situation, right? And we think that KR approaches, from what we've seen in the past, seem well suited for these tasks, and machine learning still struggles with them. Right. So that's the normal Angry Birds, but I promised to talk about open world as well. The problem is that the current competition we have, even if the AI agents can beat the humans, we still wouldn't be able to say that AI is better than humans at playing Angry Birds, because in Angry Birds, in the competition, we use a closed world. All game entities are known and fixed, right? But in the real Angry Birds game, I have some examples at the bottom here. There are constantly changes, like there's new objects, new peaks, new birds with new capabilities, new properties, new features. You have these power-ups here, and all these things that you need to do. And so basically, it's like an open world. There's constantly novelty. And this is exactly the same that happens in the real physical world, right? So when we're dealing in the real physical world, there's always novel things, always new things. Basically, every day, every hour, we see new things, right? And so in order to deal with these new things, we need these AI agents to be able to act safely in an open world, not just in a normal physical world, but in an open physical world. And this is kind of the next step we need to achieve in order to be able to really safely deal in the physical world. And what we did with this is we created a new Angry Birds competition track, the Novelty track, where we test exactly this. So we use this novelty, open world novelty hierarchy proposed by Ted Senator, and we looked at the first 3 novelties, like different class of objects, different attributes of objects, and a different representation. 0 corresponds to just different instances. That's what we have in the previous competition. And so we released some of these novelties for people to test the agent and to prepare. And in the competition, we used new ones that no one knew. So it's basically unpredictable what novelties we're going to have. And we already had 6 participants this team, and they showed quite nice performance. So these are the novelties we used. I don't want to go into the detail with them, but it's basically some previously unseen objects, some change in object features, and a change in representation. For example, the world is now upside down, right? So, and now imagine you have your AI agents, and you can see here this agent is trying to shoot in the ground, right? Because it's upside down. The agent is used to shooting like this. It cannot suddenly change to shoot like this, right? And here we have a color change, or different other changes are here. And so that's what we did in the novelty track. And so we have here 2 examples. We have one novelty. One is suddenly the peak color is now red instead of green. And most agents, a normal agent thinks, oh, there is no peak anymore. That means they have nothing to do, I have nothing to shoot. And this agent on the left is one like this. So it basically just keeps reloading because it thinks there's nothing to do. While the agent on the right, which is actually the winner of the competition, which is from University of Massachusetts Amherst, and what they're using is they use a simulator combined with causal reasoning. So they basically simulate, and then they see, oh, the outcome is different. And then they use causal reasoning to infer what might have changed that causes this difference. And then they adjust their simulator, and then they play on the adjusted simulator. And there basically, you can see they're able to see these new peaks and are able to adjust to them and to solve that. So this is kind of what we want to achieve, that agents can adjust to this novelty and deal with it, right? And now I'm almost at the end of the talk. I just want to close the loop. At the beginning, I mentioned that the spatial properties are so important in the physical world because we can basically describe before and after states of physical actions, and by doing this, describe physical interactions. And this is now for the first time what we actually did. And we presented this paper just on Tuesday, was accepted here at KR, where we use qualitative spatial reasoning to automatically describe state transitions caused by these physical interactions. Right? So now we can model these actions in the physical world automatically using spatial relations. And then if novelty occurs, we can actually see, oh, this action is not covered by the ones we've seen before. It must be a new one. And so having this new action, we can automatically then characterize what the novelty actually is. Right? So we can see here that this spatial representation and reasoning is not just useful for physical reasoning and safe physical actions and in what we described before, but it's also useful for these open world situations. Right, okay, and now I'm at the end of my talk. Sorry, I was talking a little bit faster because I noticed that my time was running short. So to summarize, we think that acting safely in the physical world is an essential capability of AI. I hope I could convince you all that this is very important. It can save lives. I've also tried to show that AIBIRDS is a very nice environment, simplified and controlled environment to test new approaches. And you can basically just pick some of these open source agents and then integrate your own methods where they get started. Right? We also saw that machine learning or deep learning approaches that are currently kind of solving most of these AI problems that don't perform very well in this problem. And KR approaches are currently superior. And this is a great opportunity for us for KR research to demonstrate our value and usefulness. And but still, we're nowhere near human capability. And we propose the methods, and you can download it and test it out to have like these individual physical reasoning capabilities to perfect these and to integrate these, and by doing this, solving the whole picture. Right? But ultimately, what we need is we need to be able to act safely in an open world, and where we have novelty that is unpredictable. And this is also covered by what we're doing here. So there's something for everyone. And yeah, that's the end of my talk. Thank you very much to my team who have been working very hard over the past 10 years on this problem. And yeah, that's it. Thank you very much.